So, okay, students, so I will continue to explain. Um, so, in the previous video, you saw that we could get this expression, right? The wall shear stress, in this case, you will get like rho u square alpha d delta by dx. Okay, so this is from the Kamran integral, and this one is for actually Blasius form. So both represents the same wall shear stress, and the alpha in this case, as you see in the previous slide. So we have the alpha in this way, right? Okay, and you remember that how I change this y to eta. Okay, so 0 to delta it becomes 0 to 1. So in case of dy it becomes delta d eta. So there the d eta is here and delta is here. Okay, I hope you all understand. So let's continue. So after you have this theta, sorry, the town or the wall shear stress, so we can modify it a little bit. Okay, so let's consider u by u infinity is equal to f. You remember that last time we talked about this is equal to f, right? And you also remember that this eta inside is actually y by delta. Okay, so if you consider this one, so what you will get, the alpha. So alpha you can write in this way, 0 to 1, right? And you will have u by u eta, so we have the f 1 minus f d eta, right? So it means if you do the integration, you will get one constant value because f is a function of eta, and you get some eta value because f you don't know right now, but you will get some eta expression, and the eta expression, for example, you got eta square example. Okay, maybe this one. So if you put the value, it should be 1 plus 2, it should be 3. It means you will get some constant value. Okay, so that's, it say that whatever f function you will have, you will get some constant value. So now let's consider your beta is another variable. In this case, beta is actually f prime at y is equal to 0. F prime we call this beta. Okay, so the 16 equation 16 so this one can be represent this one, this equation 16, this one can be reshuffled. So what is it, how we can reshuffle and reorganize in this way? So equation 16 is which one? So equation 16 is delta rho u square u infinity square alpha, then you have d delta by dx is equal to mu, you have du by dy, right, at y is equal to 0. Now if you remember last time, what is du by dy? If you remember du by dy, before we derive this one, du by dy last time, so this one can be written as du by d eta and then del eta by del y. So du by d eta in this case is u infinity f prime, because your u is actually u infinity f, so it should be u infinity f prime, and del eta by del y is nothing but g. Okay, so nothing but g. So you have this value. So if you put this value, you can see that this part is actually same here. So and this one is delta, right? And on the other hand, you will have mu is already there, but how you consider du by dy, it should be u beta by f naught delta. Okay, so this u is u infinity. So when you do the integration, you have u infinity, so this one is okay. You will have f prime is beta, so we will have this one should be okay. So beta is here. Okay, so what you don't have is this g, and in this case it has 1 by delta. So how we can relate this one? So you know that if you remember last time what I said, g, according to our definition, g was equal to eta is equal to yg, so g should be eta by y. Okay, and you also know that eta is equal to y by delta, right? So eta is equal to y by delta. That is the eta by y is equal to 1 by delta. So g is nothing but 1 by delta. So just put the value 1 by delta. So this should be here. So now you will have this expression from 16. Okay, so this equation turns to like this. So all we do, we just substitute this value du by dy in this case. Okay, so how we do is already explained. So now what we get, now you have this expression, right? Then we need to integrate this one. You need to solve this equation. Which equation? Equation number 18. You need to solve this. So how we are going to solve it? So this equation 18 can be represent in this way, but you just multiply by delta by u. Okay, and we have del by del x. You just rearrange. So I hope you will get the things. Okay, then you integrate. You will have x del eta del square by del x. But you have the one integrating constant. So of course you need to find out the integrating constant. In this case, if your delta is 0 at x is equal to 0. So if you put x0 and delta 0, your constant, this one, is actually 0. Okay, so what you will get from here, so you will get that delta square is equal to what you will get 2 mu then beta x divided by rho u alpha, and then if you want to write it in a delta form, it should be root over it. That means 1 by 2 half. Okay, so this expression you will get here. Your delta is this one, and this one can be reshuffled using in this way. Okay, you just multiply by x and then you reshuffle. You will get the things like beta is there. You have rho by mu should be nu, and then you have u infinity alpha is here, beta is here, and other rest of the thing you will have this one. You can do it. Okay, so your delta in this case 2 beta by alpha root over and then multiplied by x by root over of x. So this one you need to find it out. This amount you need to find it out. You remember that what I said, you will have some constant a, b, c, whatever it is, then x by root over of re x. So this a is just a constant, so it depends on beta and alpha. It depends on beta and alpha. Okay, so similar way, this wall stress can also be, you can write it in this way. So this you need to just differentiate delta by with respect to x. Okay, so your delta is this one, just consider this one, and then you have root over x. So if you differentiate this one, you will have 1 over 2 root x. Okay, so I already tried. So it means that delta is equal to, in this case, you will have 2 mu beta rho u alpha, then multiplied by root over x. ddx of root over x means 1 over 2 root x. Okay, then you simplify it. 2 will be cancelled out. You simplify it, and at last you will get this one. You will get, definitely you will get this one. Okay, so you just need to shuffle it. Okay, so you have rho u square alpha will be cancelled out, so not cancelled out. You will have root over of alpha. You rearrange and please try to derive. You will get this one. Okay, so I'm not showing you all the derivations, so it's simplified, but I already mentioned the way you can solve. Okay, so just differentiate delta with respect to x and then put the value here. This one you can also you can consider rex. You can differentiate this one also possible. Okay, whatever you like, at least you will get this expression. For CF is same. you already know that stress, wall stress, then half rho u square. You just substitute the value of this stress value, okay, and you reshuffle and simplify it, you will get this again. Please try to derive those things by yourself, okay. I will not do the derivation, just substitution, simplification, you will get these things. And drag force, this one is okay, just you consider this is the alpha, no need to derive this one. And if you have this FD, CF, you can also consider the average skin friction is this value. The same like before what we had the skin friction, we have the average skin friction using the Blasius formula or Blasius solution. In this case we have the Bohr-Karman integral form. Now you see that in each case we have alpha and beta, so you have to simplify it, okay. So how to simplify it? You need to get the value. So these conditions, the boundary condition, you already know what y is equal to 0, your velocity is 0 because it's no slip condition, and when y is equal to delta, your u will become the free stream velocity, right? And the stress is also when you have the y is equal to delta, your stress will be 0. It means you will have the stress only within the boundary layer. Outside the boundary layer you will not have any stress. So what you can write using, if you remember the Blasius form, you have this is stress, right? So this one is actually form 1 is proportional to the strain, right? So in this case, let's consider this is capital K and delta minus y. This is a straight line. Mx is equal to C. Mx plus C, sorry, Mx plus C, y is equal to Mx plus C. This is the form, straight line, because it's proportional, right, for the Newtonian fluid. So in this case, K is a constant, and if you can see, satisfy the condition y is equal to 0, y is equal to delta, your stress will become 0. So this satisfies the condition. So what you will do now, we will try to integrate this one. We will try to integrate. So what you will integrate here, so there's a y, so y should be here. So you can write it in this way: u mu du is equal to k delta minus y dy. Then you do the integration. If you do so, you will get this one. Again, there is an integrating constant, but you know that when y is 0, your velocity is 0, so c also should be 0. Okay, so you will not get the things that to derive fully, but you might get the small amount or some portion of it, of the derivations. Okay, so if I give like this, and then I may ask you to calculate the value of alpha and beta, okay, something like that example. So now you have this expression, right? You already know the C. So what you can do, now you substitute the value of eta delta, because you know that eta is equal to y by delta. Okay, so y is equal to eta delta, you just put the value of y, you transfer to the delta, and you divide it by mu u. Then you will get this expression from equation number 27. Okay, so why we do this? In order to express in this u by capital U form. Now you have this one already ready. Now what's the thing? Now you just change the expression to this boundary condition. So when your small u becomes capital U, your y will become delta, right? So your eta will be 1. So just put the value. So if the eta is 1, u is equal to capital U, so it means that 1 is equal to 1 is equal to you will have k delta square mu u multiplied by eta is equal to 1, and this one minus this one is half, so there is half. So it means that capital K delta square mu, then we have the k infinity should be equal to u infinity should be equal to 2. Okay, so it means that you got this expression is 2. So if this is 2, what you will get? Just put the value of 2 here. So then you will get small u by capital U, or u infinity should be 2, then 2 eta, or just write like this, 2 eta minus you will have 2 will cancel, will be eta square. So you will have this expression. Okay. You can see the we simplify the equations like this now. So if you have this one, then you just substitute the f you now you already got the f in terms of eta, right? So now go to the equation 29. This equation 13, just go to the calculate the value of alpha 13. So your alpha will be, if you substitute this eta in this case, your f, right, u by u in this case, that will be eta in this case u by u, just put the expression, it should be 2 eta minus eta square. So it means that if you put alpha is equal to integration of u by u is actually, as I said, 2 eta minus eta square, then multiplied by 1 minus 2 eta plus eta square, then integrate. If you just integrate, because now you already know the value, I mean the expression for u by capital U. Okay, so if you substitute this expression in terms of eta, so here you can see this expression u by u is like this. So fortunately this one should be, this is 2, right? So this is actually 2 eta minus eta square, that is actually this one. So if you substitute this one, you will get the alpha value, integrate it, is 2 by 15. Similar way, if you go to the equation number 17 and then want to get the beta, so again you put the value, differentiate with respect to eta, so what you will get, 2 minus 2 square, so it should be if I'm not mistaken it's 2. Okay, so you will get the beta is 2. Yeah, so what you just need to do, you need to differentiate eta in terms of only this one. You will have 2 eta square, 2 eta minus eta square. If you differentiate this one, you will get the value that is, in this case it's 2, right? And then this 2 eta, but as I said, 2 eta, but your boundary condition is y is equal to 0. So at y is equal to 0, your eta, you can see your eta is equal to what? Y by delta. So if y is 0, your eta will be 0, so it should be 0. You will have only 2 here, so that's why your beta is actually 2. Okay, I hope you understand. So now very simple thing, just substitute the value of alpha and beta in equation number 21. So if you remember equation 21, it was like delta is equal to alpha beta form. Okay, equation number 21, like this. So delta will be 2 beta alpha, so just you need to put the value of 2 and alpha, so beta and alpha, just simplify it and you will get the value is how much. You can do the root, maybe you will get 5.84, something like that. Okay, so similar way, just continue, just put the value of alpha and beta. Beta is actually 2, right, and your alpha is 2 by 15, so just put the values. You will get displacement thickness, you will get momentum thickness, okay, and you will also get the stress. It means the wall is stress. Okay, so these are the form of equation using the wall Kamran equation. So you can see that you will have different expression. One is for regarding the Blasius solution, another one is wall Kamran integral solution. So we will have two different types of expression. Similar way, all the things you got, this CF and this is the skin friction, this is the average friction. You just need to substitute the value of alpha and beta. Okay, so so we can consider the other assumptions like u is a function of y. So this could be any types of expression. Okay, so this could be any type of equation actually. And boundary condition you should know, always same, y is equal to 0, small u 0. At y is equal to 0, there will be d square u by dy square should be 0. Y is equal to delta, your small u should be capital U, and y is equal to delta, there will be no change in the velocity gradient. Okay, these are the boundary conditions, always same. And you will have these are the assumptions, as I said, u by capital U always is a function of y by delta. So this function can be given in different form. So you can try these kinds of thing, and then you will get the different expression for this delta and for other values. Okay, so in this case we just consider y by delta, but if you have different expression you will get different relationship, you will get different expression, but the way we derive is same. Okay, so how we are going to get the drag in this case? So this one is not there, but this is your task, maybe you can check. So you know that the stress is equal to F by A. So force, the drag force will be stress multiplied by A. Okay, so in this case the shear stress equation is tau, you already know this one. So frictional drag will be your area, in this case B is the breadth, in this case consider, and then you need to integrate along the length. Okay, so if the B is 1, so that is okay if you have unit width, otherwise you need to integrate along the length. 0 to L is a dx. Okay, so you just need to integrate the stress because it's a B. If you know the B, you just put it here, but most of the time the derivation, the breadth is in this case 1 unit width, and then just you integrate. So you know that the integration for the tau, you already know the value, the stress. Okay, so if you know the stress and then you integrate along the length, so you should get these kinds of thing. Okay, where is that F? Here. Okay, so you will get this FD. This is the drag force. You can see the integration, within the integration there is a L, so you have to multiply the total L. So that's how we can calculate. So we will have some expressions, so I will explain later on. So this is the way we calculate. Okay, and okay, next thing is we will have some problem solving in tutorial in the next class. So here we can see that your tau, you have the tau is two expression, right? One is this way is the expression for using the von Karman integral form, d del u del theta by del x. On the other hand, we have the expression for Blasius form, right? So in case of Blasius form, we will have du by dy at y. Okay, so it means that both are the wall stress, so both should give same result. Okay, so it means we can equate these two. So so how we are going to solve this equation? For example, sometimes they request us to calculate the delta in form of u, mu and x. Okay, how to get the value of delta in this form, u, mu and x. So it's very simple. Okay, so what we need to do, we need to use this concept that we have two different types of form. So here, if you know the theta, you differentiate with respect to x. If you know the u, you need to differentiate with respect to y at y is equal to 0. Then you need to equate these two. Okay, so if you remember last time, I give you the task to calculate the displacement thickness, momentum thickness, right? So theta is actually momentum thickness, and you know that theta you always get some constant value multiplied by delta. If you remember what you got, maybe 2 over 15 delta, or 1 over 3, 2 over 3 delta, whatever, something delta. Okay, you have some constant values. So in this slide, is the C says is constant. Okay, So it means that delta is some constant value in terms of delta, right? Then you need to differentiate with respect to x. So remember that, okay? So you need to write d theta by dx, and then we have d c delta x. So delta is a function of x, so you need to differentiate this one, or you can put it in this way. And on the other hand, you have this du by dy. Okay, so you already know that du by dy. What is du by dy? Normally we have this expression in this way. D, okay, d is a constant, right, in this case, and mu divided by rho u to the power some value. A, small b, these are actually constant values. This is just general form. So normally we represent in this way. So as I said, e is a constant, then you have the x divided by root over rex, right? X, these things are constant, this will you will get, but the power of the rex, just one we don't know. It can have different form, different values, depends on the expression. And e is also some constant, it could have different values, depends on the situation and depends on the problem solving. Okay, so if you relate this one and this one, so inside there is a delta, okay? So that delta you can actually calculate and relate in this way. Normally you will have these kinds of form, one form, two form, there are two forms, okay? So first you will get this one, and then you need to reshuffle and then do it like this. I will solve the problem, okay, later on. So honestly what I say, that if you have theta, you just expect d by dx of c theta, so you will have d by dx of c delta, and that will be equal to mu, and then you have some values, okay? So now you need to integrate opposite side, so ds will be cancelled out, so you have c delta should be equal to, you need to integrate, and then from there you will get the delta is equal to something, you will get something like that, okay? We will solve the problem, then you will understand more. So similar way, you have the cf, you already know that, you just put the value in terms of Kamran form, so rho u square del theta by dx, so this should be 2 d theta by dx. If you know the momentum equation, just differentiate with respect to s and then multiply by 2, you will get the frictional coefficient, okay? And so your theta will be c constant, so the theta value is like this. And if you have this x here, already have x, right? So you just differentiate the theta by dx, so you will have xb minus 1. Then you need to substitute this one here. This is all the general form, okay? So how to get, so you already know the theta before, you already know the delta, you have solved the delta first, and then put the delta inside the equation, differentiate it, and then put it back here, then you will get the frictional coefficient, okay? So these are the tasks for you. Let us find out the boundary layer thickness d, delta should be okay, shear stress, local drag stress, and local coefficient of frictional drag and frictional drag coefficient, okay, of the following velocity. So u by u is there a different form, so you need to solve this one for this problem, okay? So please try, and we will also discuss in the next class. Thank you very much.